Hi, I'm Ryan Baker, and this is Big Data in Education. Now we're starting week 6, which is on structure discovery. We'll start with clustering, which is a type of structure discovery algorithm. This type of method is also sometimes referred to as dimensionality reduction, based on a common application for the method, where we're trying to take a number of dimensions of data, or data points, and collapse them down to a smaller number. I actually don't think of clustering as dimensionality reduction. I think of maybe factor analysis as such, but actually there's a lot of people who use the term that way, so I thought I would introduce it. Anyways, welcome to week 7.
In clustering, you have a large number of data points. You want to find out what structure there is among the data points, and you don't know anything a priori about that structure. You don't know what that structure is going to be. It's not like prediction models where you know you want to predict a certain thing. With clustering, you don't know what the structure is, except in as much as you've picked variables that might express it. In clustering, try to find data points that group together. So, of all your data points, here are some that are similar, they're a cluster. Here's a different set that are different from those, but similar to each other. So let's take a trivial example. Let's say your data has two variables. The probability that the student knows the skill from Bayesian knowledge tracing, week 4, called Pinot, and unitized time, how fast the student's action was relative to all other students who did the same action. And I should point out that clustering works for, and it's effective in really big feature spaces, thousands, tens of thousands of data points. We're just going to talk about two so that I can actually show it on a 2x2 graph. So here we see our relatively small set of data points, and again with clustering you can use it on hundreds of thousands of data points. We've got about 40 maybe here, and we can see that they kind of are on the dimensions of Pinot and time. So the k-means clustering algorithm is the first one we'll talk about. And the k-means would say maybe these are our 5 clusters. I'll talk about how we get those clusters in just a sec. So it's going to say the green cluster is all the points that are above that line and to the left of that line that are in the green area with the green center dot. And the oranges and sections in the middle, black is bottom left, purple is bottom right, red is upright. And you can see that they each kind of define their regions, and every point on this possibility of these two variables is going to fit in one of these 5 regions. So k-means is not the only clustering algorithm. It's just the simplest. And we're going to discuss fancier ones as the week goes on. So how do we get these clusters? Well, first we decided that we wanted 5 clusters. Now, how do we do that? How do we come up with the number 5 instead of 4 or 6 or 19? More on this in the next lecture. We're going to get to it. After we had 5, we picked starting values for the centroids of the clusters. You remember those points we had, the green point and the purple point? Those are centroids. They represent the center of the space, although in fact they're not the perfect center because other spaces can impinge on it. And usually these centroids are chosen randomly to start, and then we try to find better centroids using the algorithm. Sometimes there are good reasons to start with specific initial values. For example, clusters from a different data set might provide values you want to start with in a new data set, but typically they're chosen randomly. So let's choose 5 random points, and I picked colors that for the random points kind of come up more or less like where those colors were in what I showed you earlier. So we see green is kind of up and right from a clump, black is kind of down and right from a clump. None of them are kind of at the center of clumps. And now what we're going to do is we're going to classify every point as to which centroid it's closer to. This defines initial clusters. And this is typically visualized as a Voronoi diagram, which is what you saw a minute ago. In a Voronoi diagram, you take every point and you classify it as being the centroid it's closest to, and then you draw lines equidistant between each of the centroids that represent the divisions in the space. Now, I might not have gotten this perfect. Don't complain on the forums if these things are 3 pixels to the right of where they should be, because this is just for illustrative purposes. But you can see that when you create the lines equidistant from the points, they clearly show you which cluster each point belongs to. Then we refit the centroids as the center of points in each cluster. So in other words, we set the centroids, we set the Voronoi diagram lines to split the space evenly between each of those centroids, we define the clusters based on where those centroids are, and then we move the centroids to be the center of the points in the cluster. And again, I may not get this quite right. It may be off by a few pixels, but the idea is to illustrate the ideas. So this green dot moved from the side, from the periphery to the center. Black one moved, you may remember it was below and to the right. If you don't remember, go back and take a look. And it's going to slide up and left to the center. The orange one ends up kind of in between the points. You can see that right now the orange cluster kind of has two groups that are really far apart, and you're in the center. This is not a very good cluster, and we're probably not going to end up sticking with it. And purple ends up kind of, you can see there's a real cluster, and then there's just some points, outliers out at the edges. And so purple ends up kind of in between those, and kind of at the top edge of the real cluster. Now we're going to repeat the process until the centroids stop moving, which is called convergence. So we're going to move the centroids, change the clusters, move the centroids to the center of the clusters, change the clusters, move the centroids to the center of the clusters. So if we look at this example, we see that now the lines shifted. Those 3 points that were part of the purple cluster before have now moved into the edges of the red and black because purple moved down and the distance between the centroids moved. So what happens now is we then move the points to match, and you can see that, for example, purple moved into its cluster, orange moved kind of a little bit towards one of its sides. We move the lines again, red grabs a few more points from orange. We move the centroids again, orange moved to the left, red moved to the left. Guess what's going to happen to that point on the boundary of orange and red that is now much closer to the red centroid than the orange centroid? That's right, it's going to switch. So that point moves over, and you can see that we kind of converge on clusters. Now you'll note there's some outliers still. Like that point in the very middle that is part of the orange cluster really doesn't fit the orange cluster very well. But it doesn't really fit black or purple very well either. There will be some points that end up with k-means being assigned to some cluster even if there's not a very good one. So what if we start with these centroids? Same distribution of points, it's the exact same data set, but now we start with a different configuration where orange, green, red, and black are all over to the left, and purple's over to the right. So what's the final outcome we're going to get? Well, we're not going to get very good clusters. Green and red kind of move out a little bit, but purple ends up eating both of those two clusters over to the right, because there was never a point where any of those points were closer to either of those two clusters. If you're not sure about this, you might want to hand execute this one. Play with it and see what I mean. But in other words, if you start with everything over to the left, things march over to the right a little bit, but the two clusters over to the right end up being both part of the purple cluster. And that's not a very good clustering. Red and green don't look very well designed at all. Orange looks decent, and purple looks ridiculous because it clearly has two clusters being treated as one. So what happens if your starting points are in strange places? You're going to end up with strange clustering. And this isn't trivial to avoid, considering the full span of possible data distributions. One solution, which Kanadi and Amershi use in one educational data mining paper, and it shows up a lot, is to run several times involving different starting points. So now let's do some exercises. I'm going to give a set of following examples, and what I actually want you to do is pause the slides and go and get these out of the course materials. They're going to be in PowerPoint, and work through them. Execute the k-means algorithms on these slides, and on these data sets, and on the initial point distributions. And do it by hand. You don't have to do it, totally not required, but it might be worth trying. And I should point out, by the way, don't spend a half hour getting your lines in exactly the right places. Focus on getting the concept rather than the exact right answer. The solutions that I do are by hand rather than actually using code, and so I don't guarantee they'll be perfect. The idea of this is to get the concepts, not to try to actually execute k-means by hand, because there are algorithms that do it. You can do it in RapidMiner, Weka, a lot of packages. So here's exercise 711. So here's solution step 1. We can see that we start with these initial centroids, and here's the Voronoi diagram. And guess what's going to happen? For example, the top left point is going to march down, the bottom left point is going to march up and right. They're all going to march towards the center. And that's what happens. So now we adjust the Voronoi diagram, and you can see that the center loses a lot of points. Center cluster loses a lot of points to the other clusters. And what's that mean? It means that the centroids are going to keep marching towards the center. And we adjust the Voronoi diagram again. It's starting to stabilize. And in fact, no point switch at this point, so we have convergence. So these are the final ones. The center point marched a little bit to the left, and everybody else marched towards the center. And you note, k-means did pretty reasonable for this set of points and this set of centroids. It came up with a pretty good solution. Now let's do exercise 712. You'll note in this case that we have kind of almost all the points clumped together, except for a couple outliers at the top right and the top left. What's going to happen? So what we see is that there are 5 clusters, and you can see that the initial cluster for bottom left and top left is going to kind of be such that they're going to march towards those. The center point is going to march towards the left, And those other two have 1 point exactly, so they very quickly snap to their outlier points, whereas the big cluster kind of gets split among these three. We switch the Voronoi diagram, and those points get split among those three, and they move just a little bit, and now they move just a little bit. The 2 points over the corners are in their little outlier spaces, and we've got 3 basic clusters. Now note, the 3 clusters in the same data lump might move around a little while. We could probably spend an hour kind of tweaking and moving just a little bit, and maybe a point switches here and there. But really what we have here is 1 cluster and 2 outliers. And having 5 centroids didn't really do a great job. K should be 3 rather than 5. And see the next lecture to learn more about how we pick whether we're going to have 3 rather than 5. Here's exercise 713. It's the exact same thing except for one difference. We got 1 outlier to the side rather than 2. What happens? Well, you note that that point on the side was just a little bit closer to the upper right than the upper left. So the upper right snapped down to it. The 3 clusters on the left were exactly the same, and we have 1 cluster that's completely empty. So the bottom right cluster is actually empty. And there never was a point where that centroid was actually closest to any point. This can happen sometimes. It's kind of a degenerate, weird case, and in this case you really don't want to have those 5 clusters because in fact you don't even get 1 out of it. Here's the 4th exercise. So in this case we have 4 centroids and kind of 3 data lumps. What happens? Well, you can see that the top left one kind of doesn't get anything. The bottom left one gets some stuff. The one to the right gets some stuff. What happens next is that moves just a little bit to the right, the one that's with a big data lump. The bottom left one moves to its part of it, and the right point moves to in between the 2 lumps. We move a little bit. Now the top left one has some points, and so it's going to snap down to those, even as the left point is now moving back towards that main cluster. That causes more of that middle group to become part of the right cluster, whereas the other 3 are still fighting over that 1 lump. They're now moving towards the centers of their groups, which means that now both the 2 clusters on the right now belong to that single cluster. So even though there really should be 2 clusters off to the right, we only have 1. And meanwhile, the other 3 centroids are fighting over the remaining points. The approximate solution, more or less, is that we end up with 2 lumps, 2 things that really should be clusters, clustered together, whereas 1 cluster gets split in 3. This is kind of a weird outcome, right? It didn't do very well in this case. We had unlucky initial positioning, and we ended up with something that was kind of bad. 1 data lump at the left became 3 clusters, and 2 clearly distinct data lumps at the right became 1 cluster. So here's a final exercise, 715. What's going to happen here? 1 lump, 5 centroids. And what we end up with is the Voronoi diagram keeps everything without 1 center point. And so we have 4 empty clusters and 1 cluster that actually looks like a good cluster. This actually kind of came out okay, right? As you can see, a lot depends on initial positioning and on the number of clusters. This is why we do randomized restart with new positions several times to try to make sure we don't just get unlucky once. How do you pick which final position and number of clusters to go with? If you run it 17 times, how do you know which of the 17 is the one you want to go with? Well, that's the next lecture. In the next lecture, we're going to talk about how you validate, how you decide which is the best model when you have 17 with the same number of clusters, and how you decide how many clusters to have. So thank you very much. I'm Ryan Baker. This is Big Day in Education. See you next time.